Hey everyone, and welcome. In the world of computing, we have tons of programs, or processes, all running at the same time. But how in the world do we get them to work together on the same task, without, tripping all over each other and causing total digital chaos? Well, that's what we're going to get into. Let's dive into the art of cooperation, process synchronization.
And this really gets us to the heart of it all. What actually happens when two different programs try to read and write to the exact same piece of info at the exact same time? The short answer? It gets messy, really messy.
But before we jump into the mess, let's back up and ask, why would we even want processes to share stuff in the first place? I mean, while some processes are perfectly happy doing their own thing, a lot of them are actually designed as cooperating processes. They need to interact.
And the reasons for this are actually huge. You've got information sharing, right? Like two programs needing access to the same database. You've got computation speed up, where you break a massive problem into smaller pieces for different processes to tackle at once. Then there's modularity. Think of a web server talking to a database server. And honestly, just plain convenience, like when you're editing code in one window and compiling it in another.
Okay, let's make this real with a classic example, the producer-consumer problem. Just imagine you have one process, the producer, that's making items and dropping them into a shared bucket. Then you've got a second process, the consumer, that's taking them out. To keep track of how many items are in the bucket at any time, they both share a single variable called counter. Pretty simple, right?
Well, you'd think so, but hidden inside that simple little counter is a massive potential problem. A really subtle, really dangerous bug that can bring even the most complex systems to their knees. So let's tear this thing apart and see how it can go so wrong.
The entire issue, believe it or not, boils down to these two innocent-looking lines of code. The producer runs counter ++ to add 1, and the consumer runs counter - - to subtract 1. Now you and I look at that and think it's one single unbreakable action, but to the computer, it's not.
And boom, here it is, the aha moment. What looks like one step to us is actually 3 steps for the processor. First, it has to go fetch the counter's current value from memory. Then it pulls it into a little temporary scratch pad called a register and adds or subtracts 1. Then it has to store that new value all the way back into memory. 3 separate steps.
So here's where the chaos happens. It's all about what happens when the computer switches between the producer and the consumer right in the middle of those 3 steps. Let's walk through it. Say the counter starts at 5. The producer fetches that 5 and calculates 6 in its register. But wait, before it can save that 6, the operating system interrupts it and lets the consumer run. The consumer fetches the counter, which is still 5 in memory. It calculates 4. Now the producer gets to run again and saves its 6. But right after, the consumer saves its 4, overwriting the producer's work. The final result is 4. We added 1 and took 1 away. The answer should be 5, but it's not. It's wrong. That is a race condition.
And this right here is why programmers tear their hair out. These kinds of bugs are, as the saying goes, notoriously difficult to identify and debug. Why? Because they might only happen once in a million times, only when the timing of that interruption is just perfectly, horribly wrong.
Okay, so we've got a serious problem. That little piece of code where the shared data gets touched, our counter operations, that's called the critical section. To fix this race condition, we need to establish some firm rules of the road for how processes can enter and leave this critical section.
And any good solution has to follow 3 basic rules. Number 1, mutual exclusion. Think of it like a single-person bathroom. Only one process is allowed inside its critical section at a time, period. Number 2, progress. If nobody's in the bathroom and someone wants to get in, you can't just leave the door locked. They have to be able to proceed. And number 3, bounded waiting. You can't let a process wait in line forever while an endless stream of other processes cut in front of it. There has to be a limit. So people came up with some clever ideas. One of the early classics was Peterson's solution. It's this really elegant software-only algorithm for just 2 processes that uses a couple of shared variables to perfectly satisfy all 3 rules. Super clever stuff. The problem? Modern computers, with all their fancy optimizations, are so complex that this pure software approach just isn't guaranteed to work anymore. We need something more solid.
And that brings us to a much more powerful and widely used tool, a real game changer proposed by the legendary computer scientist Edsger Dijkstra. Enter the scene, the semaphore.
At its core, a semaphore is just a special integer that comes with 2 atomic operations, wait and signal. And you can think of it like this.
Wait is like trying to get the key to a locked room, the critical section. If the key is available, you take it, the counter goes down, and you go in. If it's not, you wait. Signal is what you do when you leave. You put the key back, the counter goes up, so the next person can get in. And that's exactly how we use it. A process calls wait right before its critical code and signal right after.
Now, semaphores come in two main flavors. You've got your binary semaphore, which can only be 0 or 1. It acts exactly like that single key analogy. The room is either available or it isn't. We often call this a mutex lock. Then you have counting semaphores, which can be any non-negative number. These are perfect for managing a whole pool of resources. So if you have, say, 5 available printers, the semaphore starts at 5. Each time a process wants a printer, it calls wait, and the count goes down.
So, awesome. Semaphores seem like the perfect solution, right? We're all done. Well, not so fast. It turns out that even with a powerful tool like this, we can create new, even more bizarre problems. Let's explore this with another classic story from computer science. Picture this. 5 philosophers are sitting around a circular table. Their life is very simple. They either think or they eat spaghetti. Now, the catch is there are only 5 chopsticks on the table, with 1 chopstick placed between each pair of philosophers. To eat, any philosopher needs to pick up both chopsticks next to them, the one on their left and the one on their right.
So, let's model each chopstick as a semaphore. A perfectly logical plan would be for each philosopher to do this. First, wait on their left chopstick to pick it up. Then, wait on their right chopstick. When they have both, they eat. It seems simple, straightforward, totally logical. I mean, what could possibly go wrong?
Well, what if all 5 philosophers get hungry at the exact same moment? And I mean the exact same moment. Every single one of them reaches out and successfully picks up their left chopstick. Great. Now, every single one of them tries to pick up their right chopstick, but they can't. Why? Because it's the left chopstick of their neighbor who is also holding it and waiting. Nobody can move. They will all sit there holding one chopstick, waiting forever for a resource that will never be released. This fatal gridlock is called a deadlock. The train analogy is absolutely perfect for this. A deadlock is like 2 trains meeting at a crossing. Each one is on the other's track, and each one is waiting for the other to move. But neither can move because the other is in the way. They are permanently, hopelessly stuck. And this is one of the most serious problems you can have in concurrent programming.
And this leaves us with a really tough final question. Solving a deadlock isn't as simple as just forcing one philosopher to put down their chopstick. Because what if you always pick the same philosopher to give up their resource? They might never get a chance to eat at all, a problem we call starvation. So the real challenge is this: how do you design a system that not only avoids deadlock, but is also fair, efficient, and guarantees that everyone eventually gets what they need to make progress? Now, that is the true art of synchronization.